Welcome to Lab 5. This is the Choose Your Own Adventure lab, and the last lab. Yay! So for this lab, I decided to investigate the motion of a falling slinky. I first looked at this video, in which a slinky is shown falling with a tennis ball attached to the bottom. I thought this was a really interesting motion since the bottom of the slinky appears not to move until it collides with the top of the slinky. I put a link to this video in the description, so you can go and check out their other videos too. So I wanted to look at the motion of a slinky falling from static equilibrium. I decided that the easiest way to model the slinky falling would be to use a point particle system. Since I would only be looking at one point of the slinky for this observation, which would be the center of mass, I began to wonder if this would behave similarly to an object in free fall that just had the same mass as the slinky. However, after looking at my results, I found that this was not the case. When modeling the object in free fall, I used the fundamental principle, Newton's second law. For this equation, I took the net force on the object to only be the gravitational force. I also took the object's mass to be the same as the mass of the slinky. The initial position of the slinky's center of mass was at the origin of my axes, and I found the center of mass of my slinky to be the middle coil of the slinky. I also assumed that the initial velocity of the object would be 0 since the slinky was dropped from rest. Here's a graph of the observed data and the model data. As you can see, the observed data of the spring is graphed in blue dots, and the model data of the object in free fall is graphed with the red line. These two curves do not match up, which means that my model does not fit the observed data. This is largely due to the fact that the center of mass does not even begin to fall until 0.2 seconds after the spring is released. Therefore, I conclude that the point particle system for modeling a spring being dropped is not valid. Now, on to the questions. So first, does the slinky fall uniformly? No. To think of this, imagine a spring as many small masses, each mass being one of its coils, that are held together by small tension forces. In addition to those forces, each coil holds up the weight of the coils beneath it. This is why there are much larger spaces between the coils near the top of the spring and much smaller spaces between the coils near the bottom of the spring. The coils at the top are holding up much more weight than the coils at the bottom. Because the force on each coil is not the same, the spring does not fall uniformly. Second, would attaching a small mass, like the tennis ball in the video earlier, to the bottom of the slinky change the results, and if so, how? The spring would still behave in the same way as it did without the mass attached. The bottom of the spring would still fall only after the top of the spring met it. Thanks for watching.